We know that from the birth of the universe until today, 13.8 billion years have passed. During these 13.8 billion years, countless planets have formed throughout the universe. Some of these planets have just been born within protoplanetary disks. Some, like Earth, are in the prime of their lives. And others have long since vanished into dust along with the death of their host stars. So among the planets that still exist today, which one is the oldest ever discovered? The stars visible to the naked eye in the night sky are usually massive stars with several times the mass of the Sun or more. We know that the more massive a star is, the shorter its lifespan. So for these massive, short-lived stars, even if planets exist around them, their ages would not be very great. What about red dwarfs, these low-mass stars? They can truly be called long-lived, almost eternal. Their lifetimes can reach tens of billions, hundreds of billions, or even trillions of years. So could the oldest planets be found orbiting red dwarfs? The universe's first generation of stars should have been extremely massive stars containing no heavy elements at all. Clearly, tiny stars like red dwarfs could not have appeared that early. This has also been confirmed observationally. Almost all red dwarfs observed today are rich in metals, indicating that the material forming them must have involved earlier generations of stars. Moreover, first-generation stars lacked heavy elements, which is extremely unfavorable for planet formation. According to traditional planet formation theory, a planet must first form a metal-rich core, and only then can it rapidly grow by accretion into a sufficiently large planet. So even in metal-poor environments, planets are already rare, let alone in environments with virtually no metals. So where should we look for truly ancient planets? In fact, the general line of reasoning so far is mostly correct. For a planet to be extremely old, its host star must also be very old. So where can we find elderly stars? One promising place is globular clusters, often referred to as retirement homes for stars. The stars inside them are usually ancient elders, tens of billions of years old. Some globular clusters themselves are even older than the galaxies they reside in. It's like elderly people in real life, who personally witnessed the rise and fall of their towns. But whether massive stars, or relatively low-mass second-generation stars, all stars will eventually reach the end of their lives. Once a host star undergoes a supernova explosion, it is not entirely impossible for nearby planets to survive. In 1993, astronomers discovered a pulsar within a binary system, inside the globular cluster M4 in the constellation Scorpius. This pulsar showed clear anomalies in its rotation rate. After calculations, researchers concluded that this pulsar likely had more than one companion. At a greater distance, there might be a second companion. Given that the mass of this second companion was extremely small, only about 1% of the Sun's mass, this suggested it could be either a brown dwarf or a planet. Originally, this pulsar was named PSR B1620-26a. Its companion shared the same designation, with the suffix changed from A to B. Thus, the second small companion received the suffix C. Later, astronomers discovered that the companion with suffix B had a mass of only 0.34 solar masses, meaning it was not a neutron star at all, but a white dwarf. So it was renamed WDJ 1623-266. The object with suffix C, meanwhile, was classified as a planet, PSR B1620-26b. From this naming, we can see that this planet does not orbit the pulsar alone, nor does it orbit the white dwarf B alone, but instead orbits both of them together. That's right, this is a circumbinary system. In any case, since the stars in a globular cluster are almost all born at roughly the same time, and planets usually form alongside their host stars, this planet could be nearly as old as the cluster itself. The age of globular cluster M4 is estimated to be around 12.7 billion years. So if this planet matches expectations, its age should also be around 12.7 billion years, meaning it was born roughly 1 billion years after the Big Bang, during the cosmic dawn. As the oldest planet ever discovered so far, astronomers borrowed the name of the longest-lived person in the Hebrew Bible, and called it Methuselah, sometimes transliterated into English as Methuselah. Be careful here. This is not the same as the so-called Methuselah star, which is estimated to be older than the universe itself. That Methuselah object is a star, with an estimated age of around 14.4 billion years. Due to large uncertainties in that estimate, it does not actually conflict with the age of the universe. Returning to the planet Methuselah, its origin remains uncertain. Current research suggests that it likely did not form where it is found today. Instead, it may have been captured by the pulsar, along with another star, possibly the progenitor of the white dwarf. Planets around pulsars generally fall into several categories. They either form anew around the pulsar, are captured while passing by, or evolve from former companion stars. For this particular planet, Astronomers propose an even more complex scenario. It may have gone something like this. A planet formed together with a star, on the outskirts of the globular cluster's core. Over time, they slowly migrated toward the core. Eventually, they encountered a binary neutron star system. The incoming star, bringing its child, the planet, with it, joined the binary system as a third member. During unstable three-body interactions, one of the original neutron star companions was ejected. As a result, the system became a neutron star, a main sequence star, and a planet. Later, as time passed, the main sequence star expanded into a red giant. Its outer layers were stripped away by the neutron star. Neutron stars have a peculiar property. The more mass they gain, the smaller their radius becomes. So as matter continued to fall onto the neutron star, its size shrank while its rotation rate increased, until it completed one rotation in just a few milliseconds, becoming a millisecond pulsar. The red giant companion, after its late-stage outbursts, eventually became a white dwarf. As for the planet brought in by the original main sequence star, it now orbits both the neutron star and the white dwarf together. However, this explanation has a problem. Globular cluster M4 has an extremely low metal content. As mentioned earlier, according to traditional planet formation theory, it is very difficult for planets to form directly in such metal-poor environments. This led to another proposed scenario. Once again, we start with a close binary star system, but this time the two stars are extremely close to each other. So close that in the later stages of evolution, one star expands enough to engulf the other. As mass is lost from the system, a disk gradually forms around the pair, driven by stellar winds. This disk can extend outward to more than 100 astronomical units. When another star passes nearby, its gravitational disturbance causes material in the disk to gradually clump together, and a planet is born. Because this formation process does not require a metal-rich core as a prerequisite, it is theoretically possible for planets to form this way, even in metal-poor globular clusters. Regardless of which scenario is correct, this planet's age would not be small. It has already orbited its binary system for tens of billions of years. So will it continue orbiting like this forever, until the end of time? Because the system is still slowly drifting toward the cluster's core, and stellar density will continue to increase, hundreds of millions of years in the future. When the system again passes close to another star, its low-mass component, the planet, will be more easily ejected. As a result, this planet's ultimate fate may be to escape the globular cluster entirely, and become a rogue planet, wandering alone through interstellar space.